Welcome back to another video. So in this video, I would like to prove that L1 is a complete metric space. So recall that this is the space of every real valued sequence that is absolutely summable. So its sum is absolutely convergent. So we want to prove that this is complete. So what we need to do is start with a Cauchy sequence. So I'm going to denote that Cauchy sequence by xnr. And we're going to assume that this is a Cauchy sequence with respect to the L1 norm. So to explain a little bit more what I mean by this notation, so the R refers to which sequence it is, and then the N represents the terms of the sequence. So like if R is 1, that represents a specific sequence, so it's like x11, x12, x13, ... and each one of these is the individual numbers in the sequence. And then like if R is 2, it's x21, x22, x23. So you can think about these, as basically being the rows of an array. Each sequence is just the row of an array. And by assumption, this is Cauchy, right? So that means that, for any epsilon greater than 0, you can find a natural number n so that if I and j are greater than or equal to n, then what happens, the sum of xin minus xjn is less than epsilon, right? So basically this is saying that if you go far enough down in the array, as far as choosing your rows large enough, then if you take the difference between those sequences and you take the L1 norm, you sum it, then it's less than epsilon. And so in particular, what we want to do is we want to look at columns as well. So if we fix a specific value of n, then what we can say is that for any such I and j greater than or equal to big N, what's true is that this difference is less than epsilon. So this is just looking at the nth column of the array, and then the ith row and then the jth row, and looking at their difference. But this is definitely less than or equal to what I wrote up here, like if you take the whole sum over all the possible n, because all of these numbers are non-negative. And so that gives you that this is actually less than epsilon. And what does that mean? Well, again, if you go down a specific column of the array, every entry of that is just a real number. So for this fixed value of n, it actually tells you that xrn is Cauchy. And what that means is, what it means for it to be Cauchy, or what that implies, is that if the R goes to infinity, so if the row goes to infinity, this converges to something, some real number. So again, recalling what the array looks like, you have different rows of the array and different sequences, but we basically showed that for a fixed column, if you go down the column, the numbers kind of converge to numbers like this, right? And so this gives us actually a sequence, Sn, and now we want to do what I said at the beginning, which is we want to show, first of all, that xrn converges to the sequence in the L1 norm, and also that this sequence Sn is actually in L1. So this is what we have to do now. So the first thing, x and r converges. So what I want is that if r is big enough, this is less than epsilon. And we can get this by basically making everything finite first, and then it'll follow from that. So I'm not going to sum initially all of the values of n. I'm just going to sum to big M, let's say. And I know from before that if I do the absolute value of xin, xjn in this sum, if I sum over all the values of n for I and j large enough, that's less than epsilon. So I definitely know that this is less than epsilon. And actually, if I choose I and j potentially larger, I can make this less than epsilon over 2 if I want. So what you want to notice here is that everything here is finite. Right? I'm taking the absolute value of some numbers and I'm summing those finitely many times. And so there's nothing wrong with, in this expression, just letting j go to infinity, because I'm not dealing with infinite sums. And so if I do that, I get that this is less than or equal to epsilon over 2. And notice that I got Sn because we showed that for a fixed n, if this number goes to infinity, it converges to Sn. But this is great because now I can let m go to infinity as well, because my argument so far hasn't used anything about m, and so I can just let the m go to infinity, because this inequality is true for any m greater than or equal to 1, and that gives me that this is less than or equal to epsilon over 2, less than epsilon. Okay, so that does in fact show that Sn is the limit of xrn with respect to the L1 norm. The only thing left to show is that Sn actually belongs to L1. And we can get that using a similar technique of basically just make everything finite first, and then take limits. Okay, so in particular, we know that xrn, that this is a Cauchy sequence, and so it is bounded, right? Because every Cauchy sequence in a metric space is bounded, regardless of the metric space. So there is an r, this is just some non-negative real number, so that for any choice of little r, I get that this is less than or equal to r, right? What that, for example, means that we can use now is that if I just sum from n equals 1 to some finite big N, and again, this is for any choice of little r, that this is bounded by big R. Right, so I want to take the limit as, let's write this again. So I know that this is true. I want to take the limit of this as little r goes to infinity, because again, this is a finite sum, so I know that in here this is going to go to Sn. And so this is true for any r, and so if I take the limit, I get that this is true. And now that I approached it from this direction, I get what I want, because now I can take the limit as big M goes to infinity. I can take the limit as big M goes to infinity, and I get that this is less than or equal to r as well. So we started with a Cauchy sequence in L1, and we showed that not only does it converge in the L1 norm, but its limit is also contained in L1. And that is what we were trying to prove. Thanks for watching.